Welcome all to this week's Applied PDE seminar at the Department of Applied Mathematics, University of Washington. It's my great pleasure to introduce Dionyssis Mantzavinos from University of Kansas today. I first met Dionyssis when he still was a graduate student at Cambridge, working with Thanasis Fokas. After that, he became a postdoc at, actually was Buffalo first or Notre Dame first?
Notre Dame.
First at Notre Dame. After Notre Dame, he spent some time at SUNY Buffalo before becoming a tenure track faculty member at Kansas, where he is now. And today he'll tell us about initial boundary value problems for nonlinear dispersive PDEs in 1 and 2D. Thank you, Dionyssis.
Thank you, Bernard and Jorge and everyone for the invitation. I was thinking that I may be one of your first speakers in this seminar when you were probably still testing the waters about the online talks. I gave one talk in 2013, May or something like that. So I'm glad to be back. The title of my talk is general on purpose because I hope to convince you that what I'm going to talk about has some general applications. So the focus will be initial boundary value problems and for dispersive equations. And really what I really want to talk about is 2 dimensions. This is very recent progress, but at the same time, I'd like to review briefly some one-dimensional work as well. And so this is joint work with my postdoc mentor and collaborator, Alex Himonas from Notre Dame, and my advisor, Thanasis Fokas from Cambridge and the University of Southern California. So let me start by reminding everyone that I don't think I need to. What's a dispersive PDE? An evolution equation that describes phenomena in which waves of different wavelengths propagate at different speeds. And one of the most prominent members is the nonlinear Schrodinger equation. That's a semilinear equation. So here we see the nonlinearity is a general form here, u to the alpha minus 1 times u. And of course, the linear part, the linear Schrodinger operator here, the subscript denote derivatives as usual. And it's a universal model with many applications in mathematical physics and beyond, actually, like nonlinear optics, water waves, plasmas, and other fields. The plus is the focusing NLS, the minus is the defocusing NLS. In this talk, we will not separate between the two. Our work will be the same for both models, although they're very different, of course, in other aspects. The most famous member of this family is when alpha equals 3. This is the cubic NLS in 1 dimension. And it's famous because it's one of the prime examples of integrable systems, as was established by Zakharov and Shabbat in 72. So what does it mean to be integrable system? There is no precise definition, but one of the properties is infinitely many conservation laws, Hamiltonian structure, and importantly, the ability to linearize the equation by expressing it as a compatibility condition of a lax pair, a system of linear PDEs. The general case for alpha bigger than 1 and any natural number n for dimensions has been studied extensively via harmonic analysis techniques, since integrability is not available in general. Another very famous dispersive PDE is the KdV equation written here. There's usually also a UX term, which can be absorbed in, at least when we're thinking about the line. This goes back to the 1877 Wellposedness derivation, comes from the other equations. And what's great about it is, well, there's many things, but what made it famous initially was that it meets soliton solutions. Here's the famous such squared Seldon solution for KdV. And this equation was the starting point for the inverse scattering transform and really modern day integrable systems. This is a method that was introduced in 1967 by Garden Green, Kruskal, and Miura for the KdV initial value problem on the entire line with nice initial data. So here I should emphasize that it's KdV, which is an integrable equation. It has a lax pair, and also the data here are assumed to be nice. Nice meaning smooth enough and rapidly decaying at infinity. NLS as another integrable equation was also solved through this inverse scattering transform later on by Zakharov and Shabbat. And so one question that naturally one will ask is, what about non-integrable models? And I already hinted that there's other approaches, in particular harmonic analysis techniques, for example. And this brings us to one of the questions, one of the fundamental questions, maybe the most fundamental question that one can ask. What does it mean for a problem to be well posed, well formulated? So well-posedness is a general term that, again, has no precise definition, but it generally refers to existence of solution, that this would be the minimum, and other properties such as uniqueness and stability properties. And so in Hadamard's eyes, that's one of the most widely used definitions of well-posedness. Hadamard well-posedness refers to existence, uniqueness of solution, as well as continuous dependence of the solution on the given data, such that small changes in the data result in small changes in the solutions. So how does one prove well-posedness? For linear equations, maybe you can have an explicit solution, even for nonlinear, in fact, but in general, it's harder. And of course, typically one wants to study problems for a general class of data. For example, initial data that are in L2. Here is a fundamental result for NLS that was proved in '87 by Tsutsumi. And of course, I should say that there's many results. I'm including this as a very basic result that everyone is sort of familiar with. So this is subcritical theory in L2 in n dimensions on the whole space. And so Tsutsumi proved that this initial value problem for NLS with nonlinearity alpha between 1 and 1 plus 4 over n, where n is the number of dimensions, and initial data in L2 is globally well posed, has a unique global solution, and that solution belongs in this intersection of spaces. The first space here is what you kind of expect by looking at the initial data. So it's continuous functions from R into L2, in the t variable into L2, and then refined, this space is refined by this mixed LP space. So here R is given in terms of alpha and n by this fraction. And this is what is known, this is the famous Stricker's estimate space. So after Robert Stricker, who recently passed away, unfortunately. So this is a fundamental result that goes back to 35 years ago. It was soon after that it was extended by Cazenave and Whistler to the critical case, and also in the general case, alpha bigger than 1, and for data in Sobolev spaces HS with S positive, since S equals 0 is already L2 here. Just to remind everyone the definition of the Sobolev norm in Rn. So it's done through the Fourier transform of U0, the regular Fourier transform. And of course, this highlights the fact that the Fourier transform here allows us to take K, the Fourier variable, to be any member of Rn. Okay, so that's the fundamental result on the whole space, and of course there's many more. And another result, which is kind of a breakthrough, is on the periodic problem. That's by Bourgain in '93. who studied the cubic NLS on the torus, on the circle, in one dimension, with data in soluble spaces, HS, and proved its global well-posedness for all s bigger than or equal to 0. So this was a more challenging fact because the solution space had to be completely changed, and that's what Bourgain's huge contribution was through this work. He introduced this, or he used, there's a little bit of ambiguity there, who introduced what, but in any case, he brought to the center of attention the XSB spaces. He used them for this problem with B equals a half as solution spaces for this initial value problem. So instead of having the this Hadamard type space and then Strickert space, instead he used the XSB spaces, solution spaces. And by doing so, other people then continued working, as well as himself, continued working on proving well-posedness in XSB spaces for NLS on the real line, for KDV and other important models. And so here's how the Bourgain space norm looks like for cubic NLS. And so contrary to the Sobolev norm, when it comes to Bourgain spaces, the equation participates kind of directly impacts the norm as well through its dispersion relation. So for cubic NLS, dispersion relation is IK square, and that's what is basically showing up here. It's a norm in both x and t, and it's still defined through the Fourier transform on the whole line in x and over r in t as well. So these are some sort of results that motivate things that we will see in a bit for IBVPs. How are these results proved? A very standard way when we're talking about dispersive equations is contraction mapping method. So here's a very quick outline, as I'm sure people are familiar with, for the NLS IVP on n dimensions. And so the idea is to think of the forcing here, think of the nonlinearity as forcing. So, and then do a Picard iteration. So in particular, if you take initial data in Sobolev spaces, the first thing that one has to kind of figure out, well, not necessarily in this order, but a major thing that one has to figure out is the solution space. Let's suppose we just want to work in the Hadamard motivated solution space. So data in HS means solution as a function of x in HS, and then we want continuity over time. So in that case, the approach is always the same, no matter what the space. You first solve the forced linear problem, so replace the nonlinearity by the forcing, and of course you can do this through the usual Fourier transform in X, spatial Fourier transform. You get this solution formula. I'm using this notation here S with parameters U0 and F here. It will be convenient in a moment, but just notice that this is the usual Fourier transform we teach our students in introductory PDE class. And then you replace F by the nonlinearity, and so this solution formula becomes now a map, an iteration map for the nonlinear problem. So now this phi, this map phi applied on U is nothing but the previous formula where now F is the nonlinearity. And so the main challenge here is to determine what kind of solution space you can use such that you can prove this map is a contraction. And by doing so, of course, you get a unique fixed point and therefore a unique solution to our problem. That's the strategy. And in particular, if you have smooth data, and by this I mean Sobolev data where S is bigger than n over 2, in particular in one dimension, this would be S bigger than a half, so we would have continuous functions, at least continuous. Then by the algebra property in HS, you have this nice inequality. So you can handle products, which are what forms here the nonlinearity. You can handle them simply with this inequality, and then you can really choose your solution space to be the Hadamard space of continuous functions into HS. If your data are not as good, if S is less than n/2, for NLS, as we saw earlier in Tsutsumi's result, you have to refine your space with Strickard's estimates and Strickard's type mixed LP spaces. So this is more or less the background when it comes to initial value problems for NLS. So now let's talk about boundary value problems. Why do we care about IBVPs? I have here a few reasons, and I think there are more, but a few that at least I find interesting. First, they come up in laboratory experiments. That's immediate. You have the wave maker problem. You place a wave maker in a water tank, and you want to have some kind of boundary condition at this point. So this is, and of course the tank itself is finite. So that's a natural reason. Even more importantly, they describe physical phenomena and other phenomena actually beyond waves, if you wish, or beyond fiber optics, like the black holes dynamics are related to IBVPs as opposed to IVPs. In numerical analysis, computational mathematics, simulations are done over finite domains. So it's useful to know the properties of IBVPs in order to be able to test our new numerical schemes. And there's other applications as well, like in control theory. How does one determine the kind of boundary conditions such that a certain behavior, like let's say vanishing of solution, happens at some desired end time? So these are all boundary value problems. And here's a very simple one that one can think of solving, the nonlinear Schrodinger equation on the half line. Instead of the whole line, we go to the half line in one dimension. In one dimension, if you're thinking of the whole line, as we saw a moment ago, this is a very simple problem. We have a very clear strategy. In particular, if your data is smooth, as bigger than a half, everything is, the proof is about a page and a half. So what happens for the half line? The first obstacle that one has is, where do we place the boundary data? So sure enough, we can pick our initial data to be a Sobolev function. What about the boundary data? Can we pick it to be anything we like? Is it related to the initial data? Intuition would say it somehow has to respect the regularity of the initial data, or to reflect the regularity of the initial data, and that's true. But we don't know where to place it. And just a reminder here, or maybe not a reminder, just to refresh your memory, how does one define a Sobolev space on the half line? There's two ways we can do it. The best way, I guess, would be as a restriction of HS on the whole line. So this would be through the infimum norm. So what you do is you take all functions in HS of R, such that when restricted on the half line, they are equal to your half line function, and then you take the infimum of these norms, and that's your norm for the half line space. And that's a good definition for NES. If you have S non-negative, then you have the more intuitive definition, traditional definition of Sobolev spaces without Fourier transform, which is very helpful for us in terms of basically measuring derivatives in L2. So here we stay entirely on the half line setting. We measure derivatives in L2 up to the integer part of S. And then there is a fractional left over here. There's a remainder norm, which is defined through this cute integral here. So these are two ways to define the Sobolev space on the half line. So this is one main obstacle. Where do I place my boundary data? But really, even if we pretend this is not a problem and try to implement the methodology I showed you earlier for the initial value problem, we hit a major obstacle right away in step one. How do we solve the forced problem? We don't have Fourier transform anymore. Fourier transform is defined on the entire line. Things like sine and cosine transforms, which are nice for solving linear PDEs on bounded domains, are not very useful for obtaining harmonic analysis estimates. And so basically, there is no spatial transform that could assume the role of the Fourier transform. Even these sine and cosine transforms, in fact, are no longer options if you have non-zero boundary conditions and the order of your equation is, let's say, a third order, let's say the linear KdV. Then you don't even have those. So the question is there an analog of the Fourier transform formula that we used for the iteration map earlier in the case of IBVPs? And perhaps that's one of the reasons why IBVPs are less explored than the corresponding IVPs. Now there are two main approaches, maybe, I don't know if there's more. I know of these two main approaches in the literature on the analysis of IBVPs. The first one is by Collianer, Kenning, and Holmer. And what they do is they express the initial boundary value problem as a superposition of initial value problems. That's a very intelligent, it's a very beautiful way of doing things. It does, however, depart from the IBVP setting. And they've done a few equations, the generalized KdV and the NLS, and the KdV here, this work is on, so the first two works are in traditional solution spaces, let's say, and this one here is for when the solution space is a Bourgain space. But there hasn't been much in that direction since, I don't think so. And then the other approach is by Bona, Sun, and Zhang. And what they do is they, instead of using a spatial Fourier transform, which is not available, they use a temporal Laplace transform. So they take a Laplace transform in the t variable. And they have done a lot of work on KdV. These are just a couple of papers here. There's a lot more. And very recently on NLS, on the half-line. But the question I kind of brought up earlier still remains, what is the natural analog of the Fourier transform contraction mapping method if one is looking at IBVPs? What is that? It seems that none of these two provide a direct analog, at least in my view. And so here is something which provides an analog of the Fourier transform for linear problems. It's called the unified transform of Fokas, and several of you are familiar and have done work on it. It can handle initial boundary value problems for linear evolution equations of any order, in any dimension, and with any boundary condition which is admissible, and it leads to a well-formulated problem. And so it's like a Fourier transform, but for IBVPs, linear IBVPs. So the question that Alex Himonas asked me when I went to Notre Dame for my postdoc was, can this unified transform provide a way of analyzing nonlinear IBVPs? And so the answer is yes. And so that's some of the work we've done towards what we're hoping will be a universal method for showing well-posedness of nonlinear evolution IBVPs. So by using this unified transform as the linear solution formula, we were able to show well-posedness for NLS on the half-line. There's a few works here because of the different boundary conditions which require different treatment. Dirichlet, Neumann, and Robin very recently. KdV on the half-line and on the interval. Other equations such as the Good-Boussinesq equation on the half-line, and even non-dispersive models like the certain reaction diffusion equation. So here's, for example, a theorem for NLS on the half-line. If you have data in HS and boundary data in H2S plus 1/4, so you see what I was saying earlier, that the two spaces are connected here. With this compatibility condition between them, and if you take S to be, I should have said, S is bigger than 1/2 and less than 3/2, the bigger than 1/2 is crucial. And it has to do with the algebra property I was telling you earlier. The less than 3/2 is a technical is a technicality which can be removed. We didn't want to work harder than one we did. So, but one can remove this. This is a crucial one. So for this S and these choices of alpha, which covers, for example, the cubic NLS, you have a unique solution in the Hadamard space where the lifespan T star here is given by this formula. So it's basically 1 over the size of the data. This is a negative number up here. It's 1 over the size of the data. And the solution admits this kind of size estimate. So the solution is controlled by the size of the initial and the boundary data. And also the data to solution map is continuous, ellipse is continuous actually. So you have a full Hadamard well-posedness here. So the question then we asked was, can we use our technique for higher dimensional equations, bigger than 1 in X? And the simplest problem we thought about looking at was 2-dimensional NLS on the half space. So one of the 2 variables, x1 or x2 here is restricted on the half line, and the other one is still on the whole line. And so this is basically the focus of the rest of the talk. So of course the challenge that I described earlier is also present here. And I should say, by the way, that maybe I shouldn't go back, there's several slides, but I should say that in the 1-dimensional case, there were results by Koenig, Ponce, and Vega on the time regularity of the solution of the NLS IVP, initial value problem, but they were studying the time regularity. And these results were consistent with the regularity that we discovered was needed for the boundary data. In this case, we could not find any analogous results. So now what we want really is to know what kind of regularity the solution would have in the variables x1 and t, if that was available in the IVP setting, and we could not find anything. So really we were completely in the dark about where to place the boundary data. Of course, placing the initial data still in HS as usual, and to begin with, let's take S to be bigger than n over 2, which in this case would be 1, since we're in 2 dimensions, and then hoping to establish well-posedness in the usual Hadamard space where the lifespan is to be determined. Okay, so I talked about the first challenge, and the way that you can find, that's what the half-line taught us, the way you can find what kind of space to use is to look at the simplest possible boundary value problem. And by this, I mean the following. Of course, the first step always in contraction mapping method is to look at the forced linear problem. So here we are. That stands for the solution of a problem with initial data U0, boundary data G0, and forcing F. But you can use superposition principle to decompose this into simpler problems. So first you can separate the forcing from the data, okay? And so then you can focus on the homogeneous IBVP, and then you can separate the initial data from the boundary data. And this is a little more technical than just a superposition, but it's possible to do it. Basically, you have to extend the initial data from the half space to the entire 2-dimensional plane. You can pick an extension which is convenient such that it satisfies this kind of inequality. And by doing so, then you can think of this solution as the sum of the solution of this IVP. So this is the homogeneous IVP with data being the extension of the original initial data. And also the sum of that with this IBVP, which now has 0 initial data, 0 forcing, and some kind of boundary data, which is basically what you had before minus the IVP at the boundary. This is what it is. And so this is what we want to talk about. This is the simplest possible problem. You have 0 initial data and 0 forcing. You just focus on what's hard, which is the boundary data. And in fact, you can simplify it even more by making the boundary data to be compactly supported. And we'll see how this is nice and convenient in a moment. So we're going to focus on this problem. linear Schrodinger, homogeneous on the half plane with zero initial data, and some convenient boundary data where we don't know where these belong. We can assume they're as nice as we wish, but they're also compactly supported in time. I should have said this is in time. We don't care about the x1 variable here, but in time we want them to be compactly supported in 0t. 0t here, of course, is just any non-empty interval. Since global well-posedness follows through different techniques, all we want now is to show existence for some positive time. So Fokas's method provides this solution formula, which is for this problem is very simple. Bernard knows that this can be nasty and long, but for this problem it's just one line. So let's see how it looks like. It looks like a Fourier transform formula, but it's not, because this contour of integration with respect to the K2 variable is a contour in the complex plane. In fact, it's the positive imaginary axis and it's a positive real axis in the K2 variable. Otherwise, it's very much like a Fourier transform. Another interesting thing to note here is that this tau integral, time integral, that is, it runs from 0 to capital T, but because of the compact support of the data, if we wish, we can just replace this by R. And that's why I wanted to assume this condition here, because it's very convenient for what we're going to do in a moment. So if we parameterize along these two parts of the contour, we get two components here, the V1 and the V2. The V1 is on the imaginary axis, so you see I've replaced K2 by I K2, and that gives rise to this exponential, this minus K2 X2. That's going to be important for later. And V2 is on the real axis, so this is very much like really now like a Fourier transform kind of thing. So again, the concrete question we're asking is, where should I place my boundary data G so that this function belongs in the space HS, over the space HS, as a function of x1 and x2, and of course then continues in time. But really the main thing is we want it to belong in HS as a function of x1 and x2. So we start by estimating in this norm for V1 and V2, and then we'll see what we find. This is really how this works. We don't know. We have no hint whatsoever. So the easiest estimation is on the real axis, because you have the Fourier type exponentials, and then you can just use Parseval's theorem and the Fourier inversion. So here's the real axis component, and what is really crucial here is that it makes sense for all x2. Although this is a solution for x2 positive, as a function, this makes sense for all x2. We can consider it as a global function in x2. And so this allows us to think about it in terms of Fourier transform, and to identify it through the Fourier inversion, its Fourier transform in the variables x1 and x2 to be whatever is left over in this integrand, basically, after you remove the Fourier exponentials. That's for K2 positive. For K2 negative, it's 0, since there is nothing here. And if you know the Fourier transform, you're basically done, because what you know is if you want to measure a function in HS of the half space, it's going to be less than or equal to the norm of its trivial extension here itself on the whole space. This is by definition of the two spaces, which is defined as we saw earlier by this formula. So all we need is to know the Fourier transform, and here it is. So if we replace the Fourier transform, we get this integral here, this double integral. And if you make a change of variables, you can actually get to this point here. So here I just changed from K2 to tau, and we get to this point. And then so far this is basically exact. I mean, this is the only inequality here, which is nothing major. It's basically exact, and the only inequality I need to use is the following. I'm gonna use something very simple for this term. So we observe that actually it's not even an inequality. It's equality up to a constant. That 1 minus tau to the s, whenever tau is less than minus k1 squared, which is the situation here, and whenever s is not negative, can basically be replaced by this combination. Okay, so this is this leads to this inequality for V2. Okay, so again, this is pretty much equal here, almost equal. And here, if we expand the range of integration and also augment this integrand slightly by adding ones inside, we get these two guys, which are basically exactly what I showed you earlier, the norms of Bourgain spaces. So this was a very unexpected discovery for us, that if you want your solution, not the data, the solution to be in HS, the boundary data as a function of x1 and x2 have to be in two Bourgain spaces, the xs comma 1/4 and the x0 comma 2s plus 1/4. And if you remember what we saw earlier, 2s plus 1/4 is actually related to the data space for the NLS on the half line. So there is some connection here, of course. So the Bourgain space appears here naturally, not as a solution space, but as a space for the boundary data. So if you know, we were joking with Alex and saying, okay, if Bourgain hadn't discovered Bourgain spaces, here's a way to say that you can discover them, you know, spontaneously by studying this problem. Right. So this is what the real axis component gives you, that the data has to be in these two Bourgain spaces, and then, you know, you're hoping that this is the case. Of course, there's also the imaginary axis, and that's more challenging because the trick that worked earlier, namely that the solution part along the real axis made sense for all x2, that doesn't work anymore. This is a Laplace type exponential. It certainly cannot be extended beyond x to 0, to the left of 0, right? So this is going to lead to something which is not integrable. So instead of working with the Fourier norm of the Sobolev spaces, we go to what I showed you earlier, the physical space form of the Sobolev norm, which just measures derivatives in L2. This has several components, of course, depending also on the value of S here. Most of them are, you know, derivatives in L2, and then there is also a combination of fractional norms. I just put it here for completeness. I'm not going to show you any estimates in fractional norms. They're just ugly. They're not hard. So let's focus on the base case, which would be the L2 norm of V1. Let's see what we get then, because if this works, then there's a good chance that our conjecture about the Bourgain space as being the data space will be true. So if you estimate V1 in L2, just some straightforward manipulations give you this integral. So this is an integral over x1 of the L2 norm in x2 of the Laplace transform of this quantity. So this is a little bit kind of like a Russian doll, one into the other. Here, what we have is the Laplace transform of this integral with respect to k1. So this, let's see. Sorry, the Laplace transform of this integral, which is a k1 integral with respect to the variable k2, which will then become an x2 function. This is then measured in L2 with respect to x2, and then integrated over x1. Okay, yeah, so this is the Laplace transform that we have. So we were wondering, okay, we know that Fourier transform is an isometry in L2. What about Laplace transform? So here's a very useful lemma by Hardy that was proved 100 years ago, and says that the Laplace transform is bounded in L2 and satisfies this nice inequality. And so using this lemma, we can get rid of this L2 norm in favor of the L2 norm of the interior. That's what Hardy is telling us. And we get to that point. And then proceeding as before with the change of variables that I showed you and the trivial kind of inequalities, we can find this bound. And of course, this is exactly what we should be expecting, because previously we discovered these two spaces, but if you put s equal to 0, these two spaces become the same space, h0, x0, comma a quarter. So that's exactly what we obtain here. So the other parts of this norm are just more technical. They don't have any fundamentally different ideas, and therefore we're able to get to the same estimate for V1, and therefore by combining everything to that estimate here for V. That's again the solution of the pure linear IVVP. So this tells us that at least for the pure linear IVVP, our data should be, the boundary data should be placed in this intersection of Bourgain spaces. And that leads to this kind of conjecture for the full problem, even the nonlinear problem, if you like, that the boundary data have to belong in this intersection of Bourgain spaces, or if I should be more precise here, because we're talking about the full problem, we remove the compact support assumption, obviously. So now we need certain restriction of that global Bourgain space onto the time interval 0 capital T, but this is easy to do. So this is still a conjecture, because we have to go back and look at our decomposition and see what we've done. We have accomplished basically the estimation of this type of problem, but then the data here are not, we cannot just choose them freely. We can choose G0 and we will place it in these Bourgain spaces, but this part here depends on the initial data. It is the solution of this IVP, which, remember, the capital U0 is an extension of the initial data, which are in HS. So the question, so one has to study and make sure that the regularity of the IVP as a function of x1 and t is in the same Bourgain spaces I showed you earlier. And this is both for the homogeneous IVP and for this on this side for the force problem. It's the same type of estimates that we need. And so indeed you can prove, and that's kind of a motivation for studying the x1t regularity of the IVP, which is not traditionally studied when you show well-posedness of the IVP. You can prove that as a function of x1 and t, for any x2, any fixed x2 in R, this Bourgain norm, the two Bourgain norms together combining to this intersection space BST, are bounded by eventually the norm of the initial data, which is exactly what you need. And a similar result holds for the force problem. And so this allows us to do a contraction for S bigger than n over 2, which allows us to use algebra property and therefore prove well-posedness, local well-posedness for this problem of NLS on the half plane. So what we have here is the usual thing as far as Hadamard. We have solution in continuous functions from 0t to 0t star to HS, where t star is given by this expression and the solution is controlled by the data through this way. And also we have continuity of the data to solution map. So I have maybe a couple of minutes left. I think it was supposed to be 15 minutes plus questions, so I'll just finish with natural question. What happens when your data is not nice? What about as less than 1, in which case you don't have the algebra property? What happens then is you just need to do what people do in the case of the IVP. So you have to, basically what Tsutumi did, you have to refine your solution space, introduce LP spaces in there, and then use Tricker's type estimates. So here is what we proved. I'm not going to discuss the proof because it's messy, but you can prove well-posedness still for any s bigger than or equal to 0 and less than 1, with n's not equal to a half. So you define your P and Q through these expressions, your lifespan through this expression here, and then the solution belongs in this finer space. So you see the Tricker's type space is coming in here. and the solution is controlled by the data in this way. So this is just to show you that it works also for lab data. And so just to wrap up things, we discussed a new method for IBVPs, nonlinear IBVPs. There are well-posedness when these involve nonlinear dispersive PDEs in one dimension, and also in 2 dimensions for NLS. So of course, a natural question is, what about other equations in 2 dimensions? What about higher dimensions? So we're working on these. This is a very recent work. Also, the method works for non-dispersive equations. We've done it for reaction diffusion models. Maybe it can be done for others. Our method relies on the unified transform of Fokas, and that method was recently extended to systems of linear PDEs by Bernard and his collaborators. And so a natural question that we are very interested in is, can we use our technique to investigate the well-posedness of systems of nonlinear equations? So using basically their extension of the unified transform to study systems. And that's where I'm going to stop. So thanks for your attention.